think that's okay. I usually talk loudly, so with the microphone I have to make sure I don't talk too loudly, otherwise we get carried away. But since I have 4 hours of lectures, maybe my voice will go down slowly over time. It will improve. So I'm Bill Curtin, and I'm at EPFL in Lausanne. I'm not Swiss, you might have guessed. But I've been here in Europe for a couple of years, and it's a pleasure to have a chance to tell you about some aspects of fracture. I think this is a good summer school because you have two of the really outstanding international experts in fracture giving you lectures yesterday, Professor Brox and Professor Pinault, who have just done huge amounts of work, both in computational side, experimental side, really dealing with a lot of scales. And so I think you learned really probably a lot about fracture in those lectures. And then this morning you heard about practical assessments in a very important class of applications. So I think that sets the background for what I'll tell you about today is very different. There are many fewer detailed practical issues, but we try to go down to smaller scales and look at some of the perhaps fundamental aspects of fracture. But there are always limits. We think that going to smaller scales is better. It takes us further away from engineering. Maybe it gives us more understanding. But I think it provides, maybe it's a good balance with what you heard already in the school, and that coming last is also good because you're worn out, and so you can just sort of observe and try to absorb some of the kinds of details of things that will be somewhat new for you, because going to lower scales and thinking about problems always involves new concepts and new ideas from different areas. So it will have, some parts would have some challenges in that way. But the idea is to kind of give you a broad overview, not to give you a set of specific lessons. So with that in mind, we're talking about fracture. I'll mainly be thinking about metals as we go along. What I'll start out is, we'll see what things we get to here, but I'll start out reminding you of the fundamentals in a very loose way without doing too much, and then tell you about methods at different scales. So this is really where there's questions of physics coming in at different scales. Then I'll talk about cohesive zone models of fracture. Professor Brox probably spoke some about that yesterday. But this is one sort of the first order of multi-scale going down and putting physics in the fracture. Then I'll spend a little bit of time talking about multi-scale of fracture itself. I won't do that at the beginning. First we'll do a little bit here. Then we'll go and talk about multi-scale aspects. And then I'll tell you about specific smaller scale approaches to fracture, both dislocation plasticity and then trying to get down to atomistic scales of fracture. So this part here won't have anything to do with fracture. This will still sort of be continuum, but informed through smaller scales. This will kind of lay out what are the issues at different scales, and these will be two particular kinds of approaches that are state-of-the-art for trying to understand fracture problems. So why is this of practical importance? Well, we had a morning full of pipelines. If I look at an engineered system like an airplane, in the US used to do a lot more connection with aerospace. There are all kinds of mechanical engineering problems when you have this airplane that happens to be a US Navy airplane, but in general we're always dealing with all these kinds of engineering problems, mechanical engineering problems. But it turns out that what makes this particular airplane fall out of the sky is the wing, which is made out of a big piece of aluminum that's then cut out into these shapes, and these struts inside the wing are actually the life-critical component. And why are they life-critical? Because you drill holes in them, and inside here there are bolt holes. And at this level, this is the life-critical feature, and you can do all kinds of mechanics at this scale. You can do stress analysis, you can do finite elements of what the stresses are in the loaded bolt hole. You can do engineering analysis, and then you can do lifing. So if you have the stresses and you know how it's cycling, you can try to guess how long the plane is going to last without saying anything actually about a crack or a fracture, just kind of calibrating a mechanics problem with an experimental SN curve. But if you look more closely at the inside of the bolt hole, what you find is that there are all these little cracks. These little cracks are forming under fatigue, and it's these little cracks that are really what's limiting the life of the entire airplane. And if you really zoom in and see what these cracks look like, they tend to initiate at small particles and grow out, and then they link together, and eventually a big one becomes a fracture. But it's this process that, and ultimately what's happening at the tips of the crack here, that determines the fate of the entire airplane. So we can do engineering design sort of above this level, but ultimately it's a material problem, and we have to understand what's going on here, either to make better predictions of what's going on here, or to improve the material, not only get rid of these particles, but understand how to stop the cracks, or what kind of textures are necessary, or whether there's environmental effects, because it's this problem way down here that controls the life of the component. Okay? So we're going to try to go down and pay a lot of attention to what goes on at this scale of the crack tip. So if we remind ourselves about fracture fundamentals, if I took a sharp crack of a certain length and I apply a mode 1, a tension loading, we get a singularity at the crack tip. And you saw yesterday probably a mode 1 singularity with a square root singularity. And of course, and the coefficient of that is the important quantity for us. We'll only mainly talk about mode 1 opening fracture. We won't deal with mode 3 or mode 2, just for simplicity. And it scales with the stress and the square root of the crack length. Now the singularity doesn't really exist below some small scale. The stresses can't go to infinity. Something has to happen. But the magnitude of the singularity really determines how much energy is stored in the deformed region, and that's what controls the crack. So even though the linear approximation breaks down over some scale near the tip of the crack, if that scale is small enough, then this quantity, as if there were a true singularity, this quantity still controls the energetics of the problem. Okay? And if you take the energy and you say, well, okay, I have the energy density, and I have around a crack of approximately, I integrate the energy density around about the radius of the crack. W is just the length coming out this way to make everything dimensional. And I integrate in a cylinder. I find that the energy is this quantity squared times the crack length times per unit length, W, divided by E. And so this is the energy that's available in the field, or stored in the field, and is going to contribute to cracking. So we can characterize it in terms of K1, and the details way down here don't make too much difference. You see when I square the stress, the R singularity gets canceled out, so what's going on here really doesn't contribute a whole lot to the energy if there's a lot of energy stored in the field outside. So the energy looks like this, and the energy change if the crack grows is then just the derivative. So again goes like K1 squared. And then in elasticity, if I'm loading something by an applied load, I not only have the crack growing, but I have work done by the applied field, and it turns out that the total free energy, which includes the work done, so it includes this term plus the work done, turns out to be the negative of this term. And so there's energy released in the process that's given by the negative of this quantity here. Okay? So this means we'll lower the energy if the crack grows, but of course it costs us energy. Sometimes when people see this, they say, well, the stress is being applied far away, and so how, the displacement can't be very large, so how come this extra displacement far away contributes as much energy as is released when the crack grows? So sometimes this part, you can, of course, do the continuum mechanics and prove this to be the case, but sometimes it's hard for people to think about this. And they also tend to think, well, we usually are controlling strain in the experiment. And if you control strain, you don't have this contribution. But it turns out that if you had a fixed strain on the sample, you can think about the energy stored in a fixed strain case, and you can think about the elastic modulus change as having a crack, and you can get basically the same result as you get here. So whether you're doing applied stress or applied strain at infinity doesn't really make any difference. So creating the crack costs you some energy because you create new surface, or you have plastic deformation, you have fiber pullout. So you gain the energy by releasing the elastic field, but it costs you some energy. And we're just going to call that energy gamma per unit crack area. And the mechanism of gamma we'll come back to. But the crack is going to grow when the energy that's released is equal to the energy cost. And so when K1 reaches some value, K1C, we're going to release enough energy. And so we take the energy released, we set it equal to the energy required. This is per width of W. There's the energy per unit area. There's the amount of crack growth. Everything cancels out. And we get a critical value for the energy release that is the square root of the modulus times this energy. And this is for plane stress. And so K1C is the fracture toughness, and gamma is the fracture energy. And in fracture mechanics, I tend to think about fracture mechanics as mainly figuring out gamma. Now, there's all kinds of things one has to worry about in large-scale plasticity, but if we're thinking about small-scale plasticity, linear elastic fracture mechanics, where we don't have global plasticity, then what we can think about as fracture mechanics is mainly about finding gamma. And that is, what's the limit of the stress intensity, or what's the energy released? So this energy cost, this gamma to grow the crack, it can come from all kinds of different sources or different reasons that it costs energy. It's whatever is needed to open the crack. And depending on the material, depending on the system, there are all kinds of essentially crack tip processes that are going on. And here are some pictures of a few of them. This is crazing in polymers. So these are strands of polymer that have been drawn out over the scale of microns. And this is a dissipative process that costs you energy. And so it's going on somewhere in here. But whatever energy it costs, it's not an atomic scale process. It's not a macroscopic process. The energy cost of this is gamma. If I had a very brittle material, which I would just have to cut the atoms, and then cutting the atoms would cost me the surface energy of the material, and that could also be what controls gamma. This is a picture from some experiments we did in carbon nanotube composites. In this case, we're trying to drive a crack, and we have carbon nanotubes that are holding the crack together and dissipating energy. So it's a little bit like this process, but this is at the micron scale. This is that's 100 nanometers. So there's some sort of dissipative process associated with the nanotubes. That contributes to gamma in this system. And then in a fracture problem, we have plasticity around the crack, and there is energy dissipated here. It may not be right in the crack or at the crack tip, or like these are across the crack faces, but it's energy dissipated, and we still have to pay that energy, even though it's not really a surface energy. It's an energy dissipated in the material as the crack grows. So these are all different kinds of mechanisms that dissipate energy and that provide the resistance to crack growth. So the field is driving the crack growth, and these phenomena, whatever they are resisting the crack growth. And so at any kind of problem, the polymer physicists and material scientists worry about the energy for this process. People doing fiber composites worry about the energy for this process. In plasticity, we worry about the energy for these processes. And if we're doing ceramics, we worry about this process. Ultimately, bonds are breaking, so somewhere in here there are broken bonds, somewhere in here there are broken bonds, somewhere in here there are broken bonds. So this piece actually enters in some way in most of the other problems, and we'll come back to that. But depending on your domain, you pick the problem, and then you try to figure out what is the process for dissipating energy. We're going to concentrate on these two scales here, thinking about metals and the decohesion associated with metals. We won't talk about composites. We won't talk about polymers. But I put this to show you that they're all of the same nature at a very high-level scale, and we're worried about what gives the dissipation gamma. Okay? So if I think about modeling of fracture, I have to capture all the energy dissipating mechanisms. Right? I showed you isolated ones, but in fact, things can be going at different scales. I have to pull atoms apart, and I have plasticity, and maybe I have some other phenomena like grain boundary sliding or something. All of these phenomena contributing to the energy dissipation. And so we have to understand all of them, but they occur at different scales. And so we're worried about the behavior at the crack tip, ahead of the crack tip, in the high field ahead, behind the crack tip, what's left behind that's still holding things together, around the crack tip. So sometimes in fracture mechanics, we'll think about what happens right at the crack tip, but in reality, as you saw probably in Professor Pinault's talk, we're interested in what's going on around the crack tip. Sometimes it's behind the crack tip, sometimes it's ahead of the crack tip, sometimes it's around the crack tip. Okay? And as a consequence, this can involve many different scales, and the description of the material at each scale may be different. How we describe plasticity, how we describe fiber pullout, how we describe polymer behavior. And so it's naturally multi-scale because we have to be addressing all of these simultaneously if we don't know what things are really dissipating all the energy. So now we want to think about just methods of modeling materials. So when we're getting below a continuum scale, if you look in continuum mechanics, the one thing continuum mechanics doesn't say very much about is the constitutive behavior. Right? We conserve energy and momentum and linear momentum, and we have all of these things, and the only thing we say about constitutive behavior is it exists and it has to satisfy objectivity, which means if you rotate your head, the material behavior doesn't change, or it has to, material might have certain symmetries. But the constitutive behavior is just an input to continuum mechanics, right? But the behavior of materials, of course, depends on the constitutive behavior quite critically. Metals and ceramics are really different, not because the continuum mechanics is different, but because the constitutive behavior is different. So we have to understand what controls the material behavior, and depending on what scale we're asking about, we're going to have to understand the constitutive behavior of the material at different scales. So if we look at what kind of methods do we use at each scale, if we go down to really fundamental, we deal with quantum mechanics. And quantum mechanics really gives us how electrons interact, how atoms interact, and we can really get chemistry, where there's chemical reactions occurring. Of course, breaking bond is like a chemical reaction. You have a bond, and now it's broken, right? This is a chemical reaction. So fundamentally, if material's coming apart, creating area, breaking bonds, there's chemistry involved. Now, we don't want to deal with chemistry unless we have to, but at a certain level, sometimes we have to deal with quantum mechanics to deal with chemistry. If we don't want to do all that goes into quantum mechanics, then we can think about moving up one scale where we think about atoms. And atoms is a less expensive modeling. I'll go into detail in each of these in a minute. But then we can model things like defects, dislocations, cracks, vacancies. We can measure, we can look at their deformation, we can look at their motion. That's a hard thing to do in quantum mechanics, but in atomistics we can do it. And so this gives us more detail at a slightly larger scale, but less predictive than fundamental quantum mechanics. But still a lot of computational work. And so we can move from atomistics to mesoscopic, which is kind of a vague term. But what it tends to mean is we pay attention to the defects, not all the atoms, just the defects. And we worry about how the defects in the material move around, whether those defects are cracks, whether they're grain boundaries, whether they're dislocations. We focus on the defects, and we ignore all the other atoms, all the other things in the system. And of course, at the continuum level, we don't have atoms or defects. We just have continuum displacement fields and some sort of constitutive behavior. But the constitutive behavior came from quantum mechanics, from the existence and motion of defects, from the interaction and organization of those defects over large length scales, and that's really what ended up giving us the constitutive behavior. So depending on what level of detail we need to understand the constitutive behavior, we have to start working backwards, getting down to smaller scales. Now, when we do multi-scale modeling, there are two ways to think about problems. One is to treat each scale separately and then just take smaller scales, derive, say, constitutive behavior, and give it to the next higher scale as an input parameter. And so this is a sort of information passing. And so maybe we do quantum mechanics and we get out the structure and the lattice constants and the elastic moduli, maybe a few energies, and we pass that to an atomistic model, and we can do molecular dynamics. And then when we see how the atoms or defects are moving, we can pass that to something like mobilities or stress field around dislocations. We can pass that to a Mezzo Scale model like a dislocation dynamics model. And if we do enough dislocation dynamics, maybe we can extract out a plasticity flow law. And so we never really connect these things. We take information at each scale and try to pass it upwards. And this is the best way to go and the most efficient way to go, as long as the scales are not intimately coupled with one another. Now, the other way is to think about dealing with all of these all at once, and that's only necessary if you really have to deal with them all at once, because because one scale is not enough, and you can't pass information smoothly from one scale to the other. When you're passing information, it assumes that the model you have at this scale is the correct model, and that all you need is parameters. But this is a big assumption. The model you have at this scale may not be the right model. So sometimes you do something at one scale, and you find behavior that doesn't fit into this model. Or you find that you can't really clearly separate the two scales, so you have to deal with them simultaneously. Okay? So if you run into that problem, you really have to think about methods that deal with multiple scales simultaneously. For the moment, we're just going to try to introduce these different levels of description without worrying about multi-scale direct coupling. We'll talk about a little bit about that at the very end of the day. So let me just tell you a little quantum mechanics and atomistics and Mezzo Scale things that you may not be familiar with. So in quantum mechanics, we ultimately want to solve Schrödinger's equation. We have a system of electrons and ions. In quantum mechanics, that's all we have. We have positive charge ions, and we have electrons floating around. And we want to figure out how to minimize the energy of the system. And if you give me the ion positions, the nuclei positions, hold them fixed for the moment, then I need to solve for the energy of the electronic system. But unfortunately, this is a very coupled system. That is, I've got millions of electrons, and this is a big wave function for all the electrons. So if you look at this, you say, oh, this is just a normal sort of eigenvalue problem, some PDE piece over here, and here's the eigenvalue. But this wave function is a multi-electron wave function. And electrons are funny things. They don't behave in classical ways. And it turns out that if I have n electrons, the wave function for the n electrons has to have certain properties. Like the whole thing has to be anti-symmetric over when you switch electron A and electron B. The wave function has to be anti-symmetric. Okay? This is just a fact of quantum mechanics. And there are correlations among the electrons because they're kind of repelling one another. They're just not all behaving independently. And the potential, all the electrons are interacting with one another. So this is really a set of, it's a very big nonlinear problem. So it's almost impossible to solve. The chemists do it on small molecules, but if you want to deal with a solid, you can't solve this problem. Now, fortunately, some very thoughtful physicists figured out that, in fact, you can prove that the energy of the system is a functional only of the total electron density. The electron density, you can think of it's like a normal density, and at the moment it doesn't have anything to do with wave functions. But you can write the energy down as a function of this density, and there are different parts. There's kinetic energy of the electrons, there's interaction of the electrons with the ions, there's a Coulomb interaction, that's charge over R, that's a Coulomb interaction between the electrons. And then there's some somewhat unknown functional that deals with this anti-symmetry and deals with the correlations, but it still ultimately only depends on the density. And if you look at this, at least from a continuum mechanics perspective, say, I have an energy functional, and I have a field, a rho of R. And so the energy the system takes is the one that minimizes this energy with respect to rho of R. So if you know what this is, you can minimize it with respect to rho of R, and you can avoid solving Schrodinger's equation, but you have to make approximations for what this quantity is and actually what that quantity is. Now, the way this is done is to introduce fictitious wave functions for each electron, as if the electrons were all separate from one another. And then the density is just the square of the electron wave function. That's the density for a given electron. The total density is this. Now, these are fictitious for the moment, but it turns out if you take this and you plug it in to this equation and you try to minimize it with respect to rho of R, you're really trying to minimize it with respect to each of these fictitious wave functions. You actually get back another Schrodinger equation. But this Schrodinger equation is for one electron. And it's got some pieces to the potential here, but it's one electron and it has an eigenvalue. And this problem we can solve because this is just a straight eigenvalue problem if we know what these are. And so you solve this for the psi I, then you put them back in here and you calculate the density, and then you put that density back in here and you recalculate. And so you do an iterative approach to the problem. The outcome is, after all of this, which is done in normal kinds of numerical ways, that if you do numerical computational mechanics, you would say, well, let me expand these in Fourier series or something like this, and then try to solve this, where these are approximated by Fourier series with some coefficients. At the end, you finally get an energy for the total system, and now you have the energy of the system. And this is fundamentally, if we have the energy, we can say things about how the energy changes when we stretch the material, when we try to create a surface. So quantum mechanics, if we do density functional theory, will eventually tell us the energy of the system for a given set of ions, and then we can move the ions around and calculate the forces on the ions by taking the derivative of the energy with respect to the ion position. This is a configurational force on the ion. And then we can make the forces on the ions go to zero, and now we have the total energy of the system. So for people doing computational mechanics, once you get past the fact that this thing exists, some of the aspects are very straightforward, and there are codes to do it, but you have to understand the details. But ultimately, we get the energy of the system. And this energy is predicted without any prior assumptions, really. So you just pick elements from the periodic table and you calculate the energy. So it's really ab initio. And out of this is energy versus structure or deformation. And so here are some old examples, like this is calculating phases of silicon. So the phase of silicon that exists is the lowest energy, and the volume that it exists at tells you the volume of the unit cell of aluminum, and it turns out, of silicon, and it turns out, yes, diamond is the lowest. If you make it hexagonal, it's slightly higher energy, so in nature, what we tend to see is diamond. But it turns out if you put diamond under high pressure, you get some other phases, and you can actually see phase transformations at very high pressures in silicon to other kinds of phases. And the theory will predict all of these phases as a function of the volume, and there are very few approximations in this, and so this is a really first principles calculation of the material properties. You can predict new phases. This just happens to be a funny study of nitrogen that predicts the existence of chain-like molecules of nitrogen. But again, we're finding energy versus atomic volume, and where there's a minimum, it's locally stable. Where there's an absolute minimum, that's what we'll observe. But there are other phases that have local minima, and the local minima can change. So you can analyze all kinds of properties of materials, even properties of materials that you don't think exist, to see if they could exist under certain conditions. From a mechanics perspective, we can do things like predict the structure and the elastic constants. Here are a bunch of different predictions. It's not so important. These are lattice constants, and that's the bulk modulus. And you can see that the predictions of first principles bulk modulus are very close to experiments. And so these are different approximations that one makes, and I don't want to go into, but that one can predict the properties of simple property of material like bulk modulus. You can get more detailed and ask questions about what about impurities. I don't want to, again, go into detail, but if you look and take aluminum and you ask what's the effect of putting hydrogen into aluminum, it changes how the planes of aluminum can slip over one another, and you find that different energies for different kinds of planar faults in the material, when you add hydrogen, they can, in this case, all get lower, and that facilitates slip in the presence of hydrogen. So you don't have to guess what the hydrogen is doing. You calculate the properties of aluminum, you calculate the properties of aluminum with hydrogen, and you see that some properties of the material change, right? And this kind of thing, you can't guess what this should be, but you can calculate it. We've looked at a lot of dislocation structures. So when you look at dislocations in material, these are in magnesium. Depending on the nature of the Burgers vector, you see atomic deformations. These are just nice color plots of a certain way of looking at the atomic deformation. And this is an edge dislocation and a screw dislocation. On the basal plane of magnesium, this is a C+A dislocation, very complicated dislocation. But this is what it should look like. There is no approximation. And what this cores look like determines how the dislocations move, and that determines the plastic flow, and that determines the constitutive behavior. So we build up from here toward what's the constitutive behavior for magnesium by thinking about what the dislocation structures are. Now, there are lots of limitations to doing quantum mechanics. Even using DFT, we can only do a few hundred atoms, maybe more, but it's very, very computational. The boundary conditions, we deal with boxes. Typically, if we use Fourier series, we want to do periodic systems. Well, cracks aren't periodic, dislocations aren't periodic. So if you want to do something that's not periodic, you end up with boundary condition effects. And you have very, very small systems that are only tens of angstroms in dimensions, and you have boundary condition effects. So you have to be very careful. DFT is still not perfect, because if we go back, this thing is approximated, and the quality of the approximation, there are not really exact results for that, determines the outcome of the results, and there are other simplifications. So it can be computationally intensive to get high accuracy. So quantum mechanics is something to be done when you really have questions about chemistry, and it's also a little bit tricky because quantum mechanics calculates an energy of the total system. You cannot look in a part of the system and say the energy of this part is X and the energy of this part is Y. Right? When you do finite elements, you say the energy of this element is X and the energy of this element is Y. In quantum mechanics, all you get is the total energy. You can't partition it. So if you can't partition the energy, it's hard to see which parts of the energy are changing when you do things. And it's very hard to do multi-scale. And that's because the electrons are really these waves that spread across the entire system. So it's a very delocalized problem, and that makes it hard to do multi-scale and hard to do multi-scale coupling, because most of the methods that we tend to think about are not completely delocalized. Like finite elements is completely local. Continuum mechanics is a local theory. So we want to try to avoid doing quantum mechanics, and if we do that, then but we still want to deal with atoms, then we want to move up and think about atomistics. In atomistics, we don't worry about the electrons. We try to represent the interactions by potentials, classical potentials. They're empirical or semi-empirical, and they tell us how two atoms, which are now an ion and some electrons, will interact with one another. And simple things are like pair interactions. The total energy is the sum of the interaction of pairs of atoms, and there's some sort of model for the pair interaction, and that gives us the total energy of the system. These are usually a little bit too simple. It's recognized that quantum mechanics is important, and so there are other methods that say the energy of a given atom depends on both a pair interaction like this and a function that depends on all the other surrounding atoms and how their electron density contributes to the energy at this point. And this is called an embedding function that depends on the local electron density that all the other ones add in. These are called embedded atom methods. These are very good for metals generally, and deal with the fact that ultimately it is quantum mechanics, and this has some vestige of quantum mechanics in it, but it also makes the problem non-local. That is, the interaction energy of this atom depends on all the ones around it in a complex way, not in a simple way. Then there are other types of potentials where instead of having pair potentials, you have 3-body and 4-body potentials. These are typically done for covalent materials like silicon and carbon. These are typically done for metals, and this is typically done for just kind of simple models where you want to have atoms, but you're not too concerned about the precise detail of the interaction. But now there's no quantum mechanics to solve. This is a classical potential. This is our classical energies, and we can proceed classically by solving, minimizing the energy with respect to the positions of all the atoms without worrying about any PDEs or quantum mechanics. So if I have the energy of something, I can calculate the force by taking the configurational derivative with respect to the position of that atom. And then we can use classical statics or dynamics. Statics, we just minimize the energy. That's equivalent to making all the forces zero. And there are all kinds of numerical methods for doing that. And in dynamics, we have Newton's law. Given the force, we get the acceleration. And with the acceleration, we can evolve things forward in time. So we can either do things in statics or in dynamics, but we're moving all the atoms, and now we have a measure of the energy of the system as a function of time or as a function of boundary conditions. We can do things at finite temperature by coupling the system to an external source of heat that it can exchange energy with, and we do that with something like a thermostat. So instead of solving F equals ma, we add some sort of damping term. And the damping term tries to drive the kinetic energy of the system, which is these are the velocities of the atoms, that's just the classical kinetic energy, tries to drive it towards some desired set temperature. So you say, I want to do 300 Kelvin, so you set this to be 300 Kelvin, you evolve this equation, you keep calculating what temperature does the system have. If it's not 300 Kelvin, then I try to damp things out. And if it's greater than 300 Kelvin, I damp. And if it's less than 300 Kelvin, then this term adds energy. And so this allows us to do finite temperature. There's actually quite a lot of, there are a lot of ways to do this, and really this is in the domain of statistical mechanics, and there are lots of bad ways to do it, and there are only 1 or 2 good ways to do it. So when you turn on a molecular dynamics code and you say, set the temperature to be 300 Kelvin, you really should know what it's doing, because it could be doing the wrong thing. And so, but if you do things properly, this part is all straightforward, but this part is a little bit tricky. But if you do things properly, then you can study collections of atoms that form defects, vacancies, grain boundaries, cracks, dislocations. You can study them at finite temperature. You can apply loads and watch the defects move. You can see how the defects interact. And so this gives a lot of insight into what the fundamental defects in the material are doing. So some examples of this are defect structures like a dislocation. A dislocation is an extra plane of atoms. And here's an extra plane of atoms in an otherwise FCC crystal. And this is a Lomer dislocation. It's a singular dislocation. And here's a TEM image of the Lomer dislocation in aluminum. And here's the extra plane of atoms right here. And the atomistic model predicts this structure, and that's what you see experimentally. So if the atom interactions are good, you can get detailed information about the dislocation, about the defects in the material. Here's another example, I'll skip that. You can then also do things like fracture, so you can put a crack in the material, load it up, and what's happened here is some dislocations have been emitted, and they've come down to this boundary. These are 2 different phases, a TI3AL and a TIAL, and so you can start to measure, there's one defect here, it's a crack, it's nucleating another defect, a dislocation. That defect is interacting with another defect, which is this boundary between the 2 materials, and you can capture all of that behavior and try to extract out what's going on at the small scale that either blunts the crack or makes the crack extend. Okay? So it's this interaction of defects at different levels that's valuable about atomistic studies. One thing about atomistic simulations and fracture. So at the atomic scale, you have to be very careful about just taking a fracture geometry that looks good in a textbook and applying it at the atomic scale. Okay? Because in the atomic scale, there are scales. There is an intrinsic scale. And if I put in small crack in an atomic system, I have to apply a huge load to get something to happen. And a huge load makes other things happen. And a real crack, a larger crack, would have a much lower load. There are scales around the crack tip, like the stress intensity field is really only valid in a small region around the crack tip. If the crack tip, that region is only 4 or 5 atoms, it's very hard to decide that you're doing a valid fracture problem. So what you see in the literature a lot, coming from the continuum down, is they take a box and they put a crack in the middle by removing a few atoms, and they load it up, and they say, okay, this is a perfectly good center crack specimen, and I should be able to treat the results like I do in continuum mechanics. And this is not really true. You have to be very careful about how to do these kind of tests. And the best thing to do is to imagine that this is a semi-infinite crack, and the boundary conditions are determined by a mode 1 displacement field. So you imagine you have an infinite system with a semi-infinite crack, and somewhere out here, you apply the boundary conditions as if it was coming from infinity. You apply a mode 1 stress intensity, and then the crack tip is under mode 1, and you have everything as if it's semi-infinite. You're not modeling a semi-infinite. I mean, the atoms are not semi-infinite. You don't have an infinite number of atoms, but the boundary conditions are as if it's a long crack loaded at infinity. Then you avoid all of these finite size effects. But you'll see a lot of papers in the literature where they just say, put a finite crack in that's 20 atoms long, and they load it in tension to 5 gigapascals, and something happens, and they say, yes, this is real. It's real in the simulation, but it doesn't correlate to what happens in real materials. It's all kinds of complicated things we can look at. This is another example of dislocations with solutes. So solutes are a foreign atom in the host. The dislocation is a defect, and we can see how the dislocations interact with those defects. So atomistics gives us this ability to look at defect-defect interactions, and those defect-defect interactions control the constitutive behavior. But atomistics has its limitations. If you took a micron cubed, only a micron cubed of aluminum, it has 60 billion atoms in it. And so computationally, we can't do 60 billion atoms, and that's only 1 micron. So if you're interested in materials with a polycrystalline grain structure of 10 microns, we can't do this atomistically. So we really have to get away from atomistics. We can't model plastic zones. Plastic zones are 10, 100 microns, maybe even larger. We can't possibly capture all that atomistically. And then we still have to worry about boundary conditions because the systems can still be small. The other thing is time. If we're doing dynamics, molecular dynamics follows the vibration of atoms. And to resolve the vibrations, you have to be operating at about 1,000 times less than the period of the vibration. So that's 10 to the minus 15 seconds. So typically, when you're doing molecular dynamics, you can accumulate time of about 10 to the minus 9 seconds, 1 nanosecond. And of course, experiments are happening on seconds and hours. So there's a huge gap in time. So there's a gap in space, there's a gap in time. And then typically that means if you think about strain rates, you're applying strain rates of 10 to the 7, 10 to the 8 per second. So if the phenomena you're interested in are very time dependent, atomistics won't show you that time dependence, and you can be misled, and you have to be very careful, and sometimes you just can't do atomistics to get out the behavior. So there are limitations at every method. So if we want to get past atoms, we want to go to higher scales. And this is where Mezzo Scale comes in. And at a Mezzo Scale, you define the defects that you're interested in. Maybe they're solutes, maybe they're dislocations, maybe they're interfaces or grain boundaries, and you pay attention to the motion of the defects. You don't worry about all the other atoms. All the other atoms are just hanging around, deforming elastically and transferring load, stress from one place to another. You concentrate on the defects, because it's the motion of the defects that's going to determine the material behavior, whether the crack grows, whether the dislocation moves, whether the solutes aggregate. And so this now becomes a continuum problem. We define the defects via their stress and strain fields. This is a little bit like an Eshelby inclusion problem. You have a defect, and it has some sort of distortion in the perfect crystal, and that distortion gives rise to a stress and a strain field. So it could be like a composite. You put a particle in a composite, it generates a stress and strain field. Here we're putting in different kinds of defects, but they have stress and strain fields, and then we have to define how they move. That is, under an applied stress, how fast will they move as a function of applied stress. To do this, you have to know what's going on atomistically, but then you can not worry about the atoms and just worry about the defect itself. And so, for instance, here's an edge dislocation. There's an extra plane of atoms. We don't worry about the extra plane. We just worry about the dislocation. It generates a displacement field and singular stress fields throughout space. And we can calculate what those are in terms of the material properties, the Berger's vector, which is related to the lattice constant, the shear modulus, and the motion, the velocity of a dislocation. If I apply a shear stress or a stress to the system, it moves with a velocity that's proportional to the stress with a mobility coefficient. And that mobility coefficient is something else I measure in say, molecular dynamics. But once I've got this quantity and that quantity and this quantity, I throw away the atoms and I deal with this defect as a point defect that moves through space in response to the stress field that's acting on the defect. And this field, this defect itself will generate stresses that act on other defects. And so we calculate the interactions between the defects, and then we move them around according to the force and the mobility and evolve the system. And now we're only following the defects, not all the trillions and trillions of atoms. So the things we have to keep track of are many fewer, and we're just moving them in this case for dislocations, in a very simple over-damped way, but that's the way dislocations behave. And so we can evolve the system over much longer time scales. We can deal with many more defects, and we get away from having to deal with billions and billions of atoms. And so dislocation plasticity falls in this category where we're following dislocations moving around in the material, and we'll come back to that in another lecture. You can go to three-dimensional dislocation dynamics. Here are two dislocations that have intersected. A stress is being applied, and ultimately the dislocations break apart and plastic flow continues. And so this is forest hardening in an FCC metal, but modeled by paying attention to the interaction of the dislocations, not all the surrounding atoms. And then cohesive zone models, which is a method of trying to understand how material separates. So if I take the material and I try to separate it along a plane in some way, what's the traction, the force across the plane as a function of the displacement? And this is also a Mezzo Scale description. We're not dealing, in the end, with the atoms as a whole, each individual atom. We're trying to decide just what's the force carried across there. And I'll talk more about this later as well. So these have a lot of advantages. They're larger scales, more complex phenomena, and longer times. The disadvantages at the Mezzo scale are that the physics are governed by phenomenological rules, or you have to validate the phenomenological rules by smaller scale physics. The only things that can happen are what you put in, so nothing else can happen, and the time evolution is not as precise as it would be if you were following atoms. Sometimes these things are important, and sometimes they're not important. Any choice of studying a problem, you have to decide that these that these issues are not a problem relative to the advantage of capturing the complex phenomena and the longer times. Now, continuum mechanics, I won't spend much time on, but we really eliminate everything. We don't have any atoms, we don't have any electrons, we don't have any defects. All we have are fields and a constitutive law. So instead of having atoms, we have displacement fields. Instead of having forces, we have stress fields. Instead of defect configurations, we sort of have concentration fields, like the concentration of solutes. Okay? And then we develop the field equations by satisfying macroscopic conservation laws. But the field equations, as I mentioned, are supplemented by the constitutive laws. And the constitutive laws relate the general forces to the generalized deformations. And this is where all the information about everything else is, but it's all been collapsed into a few variables that exist in the constitutive law. So it's very efficient, but it relies on having whatever constitutive law you used has all the information about the defects has to be faithfully represented in whatever those constitutive laws are. And that is a trick or a difficulty. I won't go through the solution or getting all the PDEs out, for instance, for diffusion, for elastodynamics, for fluid mechanics. I just want to point out that there is no subscale structure. There is no scale in these equations. All subvolumes are equivalent. This is a macroscopic continuous equation for all points in space. There's not a defect here and not a defect there. It's just a continuum field that varies through space. I won't go through finite elements, just how to solve these things. I'll just come back to the multi-scale. So what I try to do is tell you a little bit about quantum mechanics, what the details are briefly, and what kind of things you can calculate. Same thing with atomistics, a little bit about Mezzo Scale, and then very little about continuum, because I think these are the new kinds of things that people aren't used to. I just want to give you the flavor of what one is able to do at these scales, roughly speaking, and what the importance is. So the importance is chemistry here, multiple defects here, complex interacting long time defects, and then field equations, which are easier to solve numerically. I'm going to skip some examples that are in there of things that we've done. I'll just say that with respect to multi-scale modeling and hierarchical modeling, if you try to, or concurrent, try to directly couple everything, the key problem is that you have interfaces between regions that are handled by different methods. So if you think about a crack, if I want to do quantum mechanics here, I can do that for a few atoms. Then I have to do, say, something with atomistics, but I can only do that over a certain scale. Then I have to do something with discrete dislocations, but I can't do that out to infinity, so eventually I have to go to a continuum method. So if I'm trying to couple all these methods together, we know quantum mechanics, we know molecular dynamics, we know dislocation dynamics, and we know continuum. So the challenge is really what goes on at the interface between quantum and atoms, or atoms and discrete dislocation, or discrete dislocation and continuum plasticity. The challenge is in coupling the two intimately, because the description of the material at each scale is completely different. And how do I put together two completely different theories, put them together intimately in a way that doesn't generate lots of errors? And if you generate errors, then you're going to get solutions that are completely wrong. So it's the transitions that are important in all of these cases. And in a lot of these problems, we have defects, as I mentioned. So you have things like a dislocation core that's just a bunch of atoms. But in discrete dislocations, that thing is sort of a line defect moving through the material. There are no atoms. And in continuum, it's just a plastic strain. There aren't even any dislocations. So how do I go from this description to that description to that description? So how does a dislocation start here, move through here, end up in here, and then become part of the plastic field? That's the other challenge with multi-scale modeling. So how do I couple things at the interfaces, and how do defects go back and forth? Okay, and we'll discuss these a little bit later. So next I'll go and talk about cohesive zone models, and then a little bit about specific back to fracture, and then a little bit, probably one of these, on modeling a fracture. So it'll take me a couple of minutes to close this, open the other files, so why don't we take 5 minutes, and then we'll talk about cohesive zone models.